Tonight, we're going to explore what scientists are finally beginning to understand inside Alpha Centauri, the nearest star system beyond our own. A place so close, in cosmic terms, that it sits almost beside us in the galaxy, and yet so far away that no human spacecraft has ever come remotely close to reaching it. By the end of tonight, you're going to understand why that might mean our nearest doorway to another world is also one of the most unsettling places in the nearby universe. There are 3 stars in the Alpha Centauri system: Alpha Centauri A, Alpha Centauri B, and Proxima Centauri, the small red dwarf that sits farther out from the bright central pair. Proxima Centauri is the closest known star to the Sun, about 4.24 light-years away. Alpha Centauri A and B are only slightly farther, about 4.37 light-years away. That sounds almost small when compared with the size of the Milky Way. Our galaxy is roughly 100,000 light-years across, so beside that, 4 light-years feels like nothing. A short step, a nearby room, the next address over. But 1 light-year is almost 6 trillion miles. So 4 light-years is more than 25 trillion miles of empty space. 25 trillion miles between us and the closest star system we could ever hope to study up close. Given that reality, Alpha Centauri should feel like the easiest place to understand. It is nearby. It is bright. It contains stars similar to our own Sun. It has at least 1 confirmed planet around Proxima Centauri. And now, modern telescopes may be starting to reveal even more hidden structure around Alpha Centauri A itself. This should be the simple one. This should be the first nearby system we fully map. The first place where we can clearly answer the deepest questions. Are there planets there? Could any of them hold oceans? Could any of them have air? Could any of them be alive? Yet instead, Alpha Centauri has become stranger the closer we look. It is a 3-star system rather than a single quiet sun. Its closest known planet circles a small flare star in only 11.2 days. One possible world may sit where temperatures could allow liquid water, while still being blasted by radiation from its star. Another possible planet around Alpha Centauri A may be enormous, faint, difficult to confirm, and hidden inside the glare of one of the nearest sun-like stars. The system that should feel familiar keeps becoming more difficult to explain. And that is the core contradiction. The closest star system to Earth may also be one of the most frustrating mysteries in reach. Close enough for our telescopes to study. Close enough to tempt every generation of scientists, engineers, and dreamers. But distant enough that even Voyager 1, the farthest spacecraft humanity has ever sent, has barely begun to show us what interstellar distance truly means. Voyager 1 launched in 1977. It has traveled for nearly half a century. It has crossed into interstellar space. It is the most distant human-made object ever built. And even after all that time, it is still only a tiny step outside our own solar neighborhood. Alpha Centauri remains tens of thousands of years away at Voyager-like speeds. That is what makes this story so unsettling. The nearest system is close enough to study, but far enough to trap us behind light, distance, and incomplete data. We can see hints. We can measure motion. We can detect tiny changes in brightness. We can block out starlight and search for faint planetary heat. But we cannot simply go there and look. At least not yet. So everything inside Alpha Centauri arrives to us indirectly, as shadows, as flickers, as missing light, as signals buried beside stars bright enough to drown out entire worlds. If you enjoy calm journeys through the stranger parts of space, take a moment to like the video and subscribe. It helps this channel reach more curious viewers who love exploring the universe slowly, quietly, and deeply. Now let's continue. Because before we can understand what may be hiding inside Alpha Centauri, we first need to understand why this system became the obvious first target in the search for another world. Before Alpha Centauri became a mystery, it became a target. That happened for a simple reason. It is nearby in the only way another star can be nearby. Alpha Centauri sits in the southern constellation Centaurus, a bright point low in the sky for observers in the southern hemisphere. To the unaided eye, it looks like a single star. Through telescopes, it separates into a pair of brilliant stars, Alpha Centauri A and Alpha Centauri B, locked in a shared orbit around their common center of mass. That shared orbit takes about 79 to 80 years. At their closest, the two stars come within roughly 11 astronomical units of each other. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. So at closest approach, Alpha Centauri A and B are separated by about the distance from the Sun to Saturn. At their widest, they spread more than 30 astronomical units apart, around the distance from the Sun to Neptune. That slow orbit gives astronomers something rare. A nearby stellar system where the two main stars are familiar enough to compare with our own, yet different enough to reveal how planets might form under another gravitational rhythm. Alpha Centauri A is the more Sun-like of the two. It is a G-type star, the same broad category as the Sun, slightly larger and somewhat brighter. Alpha Centauri B is smaller and cooler. It is a K-type star, more orange than yellow, with less light pouring into space. Together, they create one of the best natural laboratories for studying planets around Sun-like stars. This matters because most stars in the galaxy are red dwarfs, small, dim stars like Proxima Centauri. They can live for hundreds of billions or even trillions of years, but their planets often have to orbit very close to receive enough warmth. Alpha Centauri A and B offer something closer to the environment we already understand. A planet around one of them could orbit at a more comfortable distance. Its year could be measured in months or years instead of days. Its sky could be lit by a star with a steadier, more familiar glow. That possibility has made Alpha Centauri irresistible for generations of planet hunters. A planet there would be close enough for repeated study. Astronomers could return to it again and again with newer instruments. They could measure its orbit more precisely over time. They could watch how its signal changes as it moves around its star. For a planet hundreds of light years away, many details remain painfully faint. A tiny dip in starlight may be all we get. A slight wobble in the star may suggest the planet's mass. A trace of color in the light may hint at an atmosphere. Around Alpha Centauri, the same clues become more valuable because the system is so close. 4.37 light-years still means more than 25 trillion miles. Yet for astronomy, that distance is almost intimate. Light from Alpha Centauri reaches Earth after a little more than 4 years. Light from a planet 1,000 light-years away began its journey before many modern nations existed in their current form. A planet around Alpha Centauri would belong to our immediate stellar neighborhood. It would be close enough for long campaigns of observation. Close enough for careful comparison with Earth, Venus, Mars, and the outer planets. Close enough that future telescopes could search for heat, reflected light, orbital motion, and perhaps one day, the chemical fingerprint of an atmosphere. That is why Alpha Centauri keeps pulling attention back toward itself. It offers the nearest possible test of a deep idea. If planets can exist around stars like the Sun, and if one of the nearest Sun-like systems contains them, then Earth may belong to a much larger pattern. A nearby rocky world around Alpha Centauri, A or B, would instantly become one of the most important discoveries in astronomy. It would turn the nearest stellar neighbor into a real destination. Something map-like, something measurable, something future missions could aim toward. For that reason, Alpha Centauri has always felt like the first doorway, the first serious place to look beyond our own solar system, the first nearby system where another Earth might reasonably be hiding. Then the simple picture starts to break apart, because Alpha Centauri is familiar only from a distance. Inside the system, the architecture is far more complicated than a single sun with planets moving quietly around it. From Earth, Alpha Centauri appears almost deceptively simple. To the naked eye, it shines as one bright point in the southern sky. For much of human history, that was all anyone could see. A bright star in Centaurus, useful for navigation, beautiful through the clear air of the southern hemisphere. Then telescopes revealed that the point was divided. Alpha Centauri was actually two bright stars moving around each other. The brighter member became Alpha Centauri A. The slightly dimmer companion became Alpha Centauri B. They form a binary star system, which means two stars bound together by gravity. Neither star simply sits still while the other circles it. Both orbit around a shared center of mass. That center lies between them, like an invisible balance point in space. Their orbit takes almost 80 years to complete. During that long cycle, the distance between them changes dramatically. At their closest, they come within roughly 11 astronomical units. That is about the distance from the Sun to Saturn. At their widest, they separate by more than 30 astronomical units. That is roughly the distance from the Sun to Neptune. So the heart of Alpha Centauri is a slow, massive gravitational dance. Two sun-like stars moving through a space wide enough to contain much of our outer solar system. Alpha Centauri A is the larger and brighter star. It is similar to the Sun in temperature and color, though a little more massive and more luminous. Alpha Centauri B is smaller and cooler. Its light is more orange, and it gives off less energy than A. Together, they create the familiar part of the system, the part that makes planet hunters lean forward, the part that makes Alpha Centauri feel like the natural place to search for another Earth. But the system extends farther out, much farther. At an enormous distance from the bright pair is Proxima Centauri. Proxima is a red dwarf, a small cool star with far less mass and light than the Sun. Red dwarfs are the most common stars in the Milky Way. They burn their fuel slowly, which allows many of them to live for hundreds of billions or even trillions of years. Proxima is tiny compared with Alpha Centauri A. It has only about 12% of the Sun's mass. Its visible light is so faint that it cannot be seen with the unaided eye from Earth. Yet this dim little star is the closest known star to the Sun. Its distance is about 4.24 light years. That is slightly closer than Alpha Centauri A and B, which sit about 4.37 light years away. The name Proxima comes from Latin. It means nearest. That name fits because Proxima sits at the edge of the Alpha Centauri system, like a faint outer ember. It is thought to orbit the central pair from a very wide distance. Its path may take hundreds of thousands of years to complete. That scale is difficult to picture. Alpha Centauri A and B complete their shared orbit in a human lifetime. Proxima moves around them on a timescale longer than entire civilizations. This changes the feeling of the system. Alpha Centauri is a neighborhood with layers. At the center are two bright stars, close enough to tug strongly on each other. Far outside them is a small red star, faint enough to hide from the human eye, yet important enough to carry the nearest confirmed planet beyond our solar system. That architecture matters. Any planet around Alpha Centauri A must survive while Alpha Centauri B moves through its long orbit nearby. Any planet around Alpha Centauri B faces the same shifting influence from A. Any planet around Proxima lives in a completely different environment, close to a small active star on the outer edge of the system. So the first simple hope begins to change shape. A planet inside Alpha Centauri would belong to a system where more than one star shapes the sky. Gravity would come from different directions across long stretches of time. Starlight could vary depending on where the stars are in their orbit. Stable places may exist, but they have to be carved out carefully. That is why Alpha Centauri becomes so fascinating. The nearest stellar system to our own contains familiar stars, a faint outer companion, and enough gravitational complexity to make every possible planet more difficult to understand. The doorway still looks inviting from Earth. Inside it, the architecture is already starting to twist. At the center of Alpha Centauri, the mystery becomes physical. Alpha Centauri A and Alpha Centauri B are not empty lights in the sky. They are enormous spheres of plasma. Plasma is gas heated so intensely that electrons separate from atoms, creating a glowing mixture of charged particles. Alpha Centauri A is the more familiar of the two. It is a G-type main sequence star, the same broad class as the Sun. It has about 1.1 times the Sun's mass. Its radius is about 1.2 times the Sun's radius. Its brightness is roughly 1.5 times greater than the Sun's. Inside it, the central engine is nuclear fusion. In the core, hydrogen nuclei are squeezed together under extreme pressure until they fuse into helium. That process releases energy because a tiny amount of mass is converted into light and heat. Einstein's equation, E equals mc squared, describes that exchange. A small amount of mass becomes an enormous amount of energy. The core of a sun-like star reaches roughly 15 million degrees Celsius. At those temperatures, matter does not behave like anything on Earth's surface. Atoms are stripped apart. Particles collide at tremendous speeds. Radiation is born in the dense central region, then begins a long journey outward. A photon created in the core does not fly straight into space. It scatters again and again through the thick interior. Inside a star, the material is so dense that light can be absorbed and re-emitted countless times before escaping. Energy may take thousands to hundreds of thousands of years to work its way from the core to the surface. By the time it leaves as visible starlight, the energy has been reshaped by layer after layer of stellar material. Alpha Centauri, likely has a radiative interior around its core, where energy moves mainly through radiation. Farther out, it has a convective outer layer. Convection means hot material rises, cools near the surface, then sinks again. A pot of boiling water gives a simple comparison. Hot water rises from below, releases heat, then falls back down. In a star, that circulation happens in plasma instead of water. The surface we see is called the photosphere. It is the layer where light finally escapes into space. For Alpha Centauri A, that light has a slightly familiar color because its surface temperature is close to the Sun's. Alpha Centauri B is built on the same basic principle, but with different proportions. It is a K-type main sequence star. It has about 90% of the Sun's mass. Its radius is smaller than the Sun's. Its brightness is only about half the Sun's. Its surface is cooler, so its light has a warmer orange tone. Inside Alpha Centauri B, hydrogen also fuses into helium in the core. Since the star is smaller, the pressure and temperature conditions differ from Alpha Centauri A. It burns fuel more slowly. Its outer convective region is thought to reach deeper. That matters because convection helps shape magnetic activity, star spots, and subtle variations in brightness. Star spots are cooler, darker patches on a star's surface, created by magnetic fields. The Sun has them. Alpha Centauri B has them too. Those surface features can make planet searches more difficult because they create small changes in the star's light that can imitate or hide the signal of a planet. So the interior of Alpha Centauri already affects the search for worlds around it. Fusion creates the light. Convection shapes the surface. Magnetic activity adds noise. Brightness creates glare. Everything scientists want to know about hidden planets begins with understanding the stars themselves. That is the strange first answer to what lies inside Alpha Centauri. At its center are stellar cores turning hydrogen into helium. Around those cores are layers where energy slowly fights its way outward. At the surface are glowing photospheres bright enough to reach Earth after more than 4 years of travel. The stars are familiar enough to compare with the Sun, but powerful enough to bury nearby planets inside their light. To find what else is hidden there, scientists first have to read stars they can never enter. Scientists can describe the inside of Alpha Centauri without ever touching it. The method begins with light. Every star sends out a mixture of colors, and when that light is spread apart, it creates a spectrum. A spectrum is like a barcode made of light. Certain colors appear brighter. Certain narrow lines appear darker. Those lines come from atoms absorbing specific wavelengths. Hydrogen leaves one pattern. Helium leaves another. Iron, calcium, sodium, magnesium, and other elements leave their own signatures. This is how scientists know what stars are made of from trillions of miles away. Alpha Centauri A and B both show the chemical fingerprints of ordinary stars, mostly hydrogen and helium, with smaller amounts of heavier elements mixed in. Astronomers call everything heavier than helium a metal, even elements like oxygen or carbon. That can sound strange, but in astronomy, the word metal is a shortcut for the heavier ingredients forged by earlier generations of stars. Those ingredients matter because rocky planets need them. Iron builds cores. Silicon and oxygen build rock. Carbon, nitrogen, and phosphorus help build the chemistry associated with life on Earth. So reading Alpha Centauri's spectrum does more than describe the stars. It also hints at the raw material available when planets formed around them. Scientists also measure brightness and temperature. A star's color reveals its surface temperature. Blue stars are hotter, red stars are cooler. Yellow-white stars like the Sun and Alpha Centauri A sit between those extremes. Alpha Centauri B glows with a cooler orange tone. Once astronomers know a star's brightness, temperature, and distance, they can estimate its size. Once they know how two stars orbit each other, they can calculate mass. That is especially useful for Alpha Centauri A and B because their 80-year orbit gives scientists a natural scale. Gravity becomes a measuring tool. The way the two stars move reveals how massive they are. Their mass then helps scientists model the pressure, temperature, and fusion rate inside them. There is an even subtler method. Stars vibrate. Their surfaces rise and fall in tiny patterns caused by sound waves moving through the interior. This field is called asteroseismology. The word means star-quake study. It is similar in spirit to how geologists use earthquakes to study Earth's interior. On Earth, seismic waves pass through rock at different speeds depending on density and composition. Inside a star, waves move through plasma. Their rhythm reveals clues about the star's density, age, rotation, and internal layers. For Alpha Centauri A, these vibrations have helped refine estimates of its age and structure. The system is thought to be older than the Sun, likely around 5 to 6 billion years old. The Sun is about 4.6 billion years old. That matters because older stars have converted more hydrogen into helium in their cores. Their internal structure changes slowly as fusion continues. A star may look steady from Earth, while its center quietly evolves across billions of years. This is the deeper meaning of reading Alpha Centauri. Scientists are using surface light to infer buried cores. They are using color to measure heat. They are using motion to weigh stars. They are using vibrations to probe layers no spacecraft could survive. Yet every method begins with the same overwhelming source of information: starlight. That starlight tells us what Alpha Centauri is made of. It tells us how hot the stars are. It tells us how they move, age, burn fuel, and shape the space around them. The same light also creates the next problem. Any planet near Alpha Centauri A or B has to be found inside the glare of the very stars that make the system readable. The better scientists understand the stars, the clearer the difficulty becomes. A planet may be there. A rocky world may be orbiting quietly. A giant planet may be glowing faintly in infrared. But before Webb or any future telescope can reveal it, the star's own light has to be controlled, reduced, and carefully removed. That is where the James Webb Space Telescope enters the story. Webb launched on December 25, 2021 from French Guiana, riding an Ariane 5 rocket away from Earth. It now operates about 1 million miles from our planet, near a gravitational balance region called Lagrange Point 2. At that distance, Webb can keep Earth, the Moon, and the Sun behind its large sunshield, while its cold instruments stare outward into deep space. Most people think of Webb as a telescope built to see the early universe, ancient galaxies, distant nebulae, light stretched by the expansion of space. But Webb is also powerful enough to study nearby worlds and nearby stars in a completely different way. For Alpha Centauri A, the key instrument was the mid-infrared instrument, usually shortened to MIRI. Mid-infrared light is invisible to human eyes. It comes from cooler objects that glow with heat rather than visible brightness. A star like Alpha Centauri A still shines strongly in infrared, but a giant planet can also give off detectable warmth. That makes mid-infrared observing useful for a very specific kind of search. Astronomers can look for a faint warm object near a brilliant star. In the case of Alpha Centauri A, that meant trying to find a possible planet buried in the glow of the closest sun-like star system to our own. Webb had to make the star less overwhelming before it could search the space around it. To do that, MIRI used a coronagraphic mask. A coronagraphic mask is like a tiny artificial eclipse built into the telescope. It blocks the brightest part of the star's image so the instrument can look for dimmer objects nearby. The idea sounds simple. In practice, it is delicate. Alpha Centauri A is bright enough to challenge even Webb. Its companion, Alpha Centauri B, adds another nearby source of light. The pair also sits so close to Earth that it moves noticeably across the background sky over time. This motion is called proper motion. It means the star's position shifts against more distant background stars because it is relatively close to us. Alpha Centauri's proper motion is measured in arcseconds per year. An arcsecond is a tiny slice of sky, 1/3600th of a degree. For most distant stars, that kind of motion is tiny across human timescales. For Alpha Centauri, it matters enough that Webb's observations had to account for it carefully. The telescope also had to manage its own limitations. Webb is extremely sensitive to heat. Its instruments are designed to detect faint infrared signals, so unwanted warmth can become noise. The telescope has to point with extraordinary stability. The star has to be placed behind the coronagraph with great precision. The observations have to be planned so the faint signal of a possible planet can be separated from leftover starlight, instrument patterns, and background objects. Researchers used a custom observing sequence for this reason. They could not simply point Webb at Alpha Centauri A and take an ordinary image. They had to observe the star in a controlled way, use the coronagraph, compare images, subtract unwanted light, and search the remaining data for anything that moved or glowed like a planet. This is the strange patience of modern astronomy. A planet can enter the data as a tiny excess of warmth, a slight point in the residual image, a faint source that remains after the bright star has been mathematically reduced. The telescope does not hand scientists a clean picture of another world, with clouds and colors and oceans. It gives them patterns. It gives them differences between one observation and another. It gives them a signal that must survive every test researchers can throw at it. Around Alpha Centauri A, that careful process produced something extraordinary. A faint object appeared in the region where a planet could exist. It was far dimmer than the star. It sat inside one of the most difficult observing environments in nearby astronomy. And for a moment, the nearest sun-like star seemed to have revealed a hidden companion. The discovery should have made the picture clearer. Instead, it opened a stranger problem. Because the possible planet appeared once, then slipped back into uncertainty. The faint signal around Alpha Centauri A was extraordinary because of where it appeared. It seemed to sit near the closest sun-like star beyond our own solar system. Alpha Centauri A is only about 4.37 light-years away. That means the light Webb captured had been traveling for a little more than 4 years before it reached the telescope. For astronomy, this is almost immediate. Many exoplanets are found hundreds or thousands of light-years away. Their light began traveling toward us during earlier chapters of human history. Alpha Centauri is different. It belongs to the immediate stellar neighborhood. A discovery there would feel almost personal. The candidate Webb detected was described as a possible gas giant. A gas giant is a large planet made mostly of hydrogen, helium, and other gases, more like Jupiter or Saturn than Earth or Mars. Jupiter is about 11 times wider than Earth. It has no solid surface that a spacecraft could stand on in the ordinary sense. As you descend into Jupiter, the atmosphere grows thicker and hotter until gas becomes a crushing fluid deep below the cloud tops. A world like that can be scientifically valuable, even when it feels nothing like home. That is part of what made the possible Alpha Centauri A planet so strange. The object appeared in the region around the star where temperatures could allow liquid water under the right conditions. This region is called the habitable zone. It is sometimes nicknamed the Goldilocks zone because a planet there receives enough starlight for warmth without being placed too deep into the star's heat. Around the Sun, Earth sits comfortably inside this region. Venus sits closer in, where sunlight is stronger. Mars sits farther out, where sunlight is weaker. Around Alpha Centauri A, the habitable zone would be positioned according to the star's brightness. Since Alpha Centauri A is brighter than the Sun, its habitable zone would sit farther out than Earth's orbit around the Sun. That sounds promising at first. A planet in the habitable zone of the nearest Sun-like star would be one of the most important objects ever found. It would become a natural target for future observatories. It would be studied again and again. Its orbit, temperature, brightness, and possible surroundings would become part of a new map of the nearest star system. The problem is the type of planet. A gas giant in a habitable zone is very different from an Earth-like planet in a habitable zone. Earth has a rocky surface. It has oceans resting on a crust. It has an atmosphere thin enough for sunlight to reach the ground and thick enough to hold warmth. A gas giant is a moving atmosphere thousands or tens of thousands of miles deep. Its winds can circle the planet at extreme speeds. Its cloud layers can be stacked across many pressures and temperatures. Its interior may become metallic under enormous compression. If this candidate is real, it would be inhospitable to life as we understand it. There would be no open ocean on a solid surface. There would be no continent under a blue sky. There would be no familiar shoreline where chemistry could unfold in a way that feels Earth-like. The planet itself would be more like a nearby Jupiter, placed in the most interesting possible orbital region. Even detecting it was difficult. The candidate appeared more than 10,000 times fainter than Alpha Centauri A. That means the star was still overwhelmingly brighter, even after Webb used its coronagraph to reduce the glare. A difference of 10,000 times is the kind of contrast that turns a possible planet into a delicate signal. A small patch of warmth has to survive the glare of the star, the glow of the telescope, the processing of the data, and the motion of the system across the sky. This is why scientists treat the result carefully. The signal is strong enough to be exciting. The system is close enough to be historic. The possible planet sits in a region important enough to change how we think about Alpha Centauri. Yet the first object Webb may have pulled from the glare is already more complicated than the phrase habitable zone suggests. That phrase makes the imagination reach for oceans, clouds, and a second Earth. The candidate itself points towards something larger, colder, heavier, and stranger. And if a giant planet can hide there, inside the light of Alpha Centauri A, then the next layer of the mystery becomes even more unsettling. A world can appear once in the nearest sun-like system, then refuse to become simple. A gas giant in the habitable zone changes the meaning of the discovery. The phrase sounds gentle at first, It makes the mind picture a blue world. Clouds, oceans, weather moving over continents. A place where sunlight falls on rock and water. A gas giant belongs to a different category of planet. Jupiter gives the clearest comparison. It is about 318 times more massive than Earth. Its visible surface is really the tops of clouds, made mostly of ammonia ice and other compounds. Below those clouds, the atmosphere grows thicker with depth. Pressure rises, temperature rises. Hydrogen gas becomes compressed into stranger forms. Deeper still, scientists think Jupiter may contain metallic hydrogen, a state where hydrogen behaves more like an electrically conducting metal because the pressure is so extreme. A spacecraft entering that kind of world would never find a beach or a plane. It would descend through clouds, winds, darkness, heat, and crushing pressure. Saturn follows the same broad pattern. It is lower in density than Jupiter, famous for its rings, and made mostly of hydrogen and helium. Its atmosphere has powerful jet streams. Its north pole contains a strange six-sided storm system called the hexagon, wide enough to fit several Earths across. These planets are beautiful. They are scientifically rich. Their environments are profoundly unlike the solid worlds where familiar life takes hold. So if the Alpha Centauri A candidate is real, its importance would come from a different kind of promise. It would show that a large planet can exist in a stable region, around one star inside a binary system. That matters because Alpha Centauri A does not live alone. Alpha Centauri B moves around it across an 80-year orbit, sometimes coming as close as about 11 astronomical units. In our solar system, that distance would place it a little beyond Saturn, a planet around Alpha Centauri. A would need to hold its orbit, while another star slowly changes position in the same system. Astronomers call this kind of path an S-type orbit. The planet orbits one star, while the second star remains a distant companion. Stable S-type orbits can exist in binary systems, especially when the planet stays close enough to its own star. The outer regions become more vulnerable because the companion star can tug over long spans of time. That tug can stretch an orbit. A stretched orbit is called eccentric. The more eccentric an orbit becomes, the more uneven the planet's heating can be as it moves closer to and farther from its star. A large planet surviving in the right zone around Alpha Centauri A would give scientists a real example to compare with those models. It would say something about how planets form inside a system with two bright stars. It would also make moons more interesting. In our solar system, giant planets carry entire families of moons. Jupiter has more than 90 confirmed moons. 4 of them are large enough to be worlds in their own right. Io is covered with active volcanoes. Europa likely hides a salty ocean beneath an ice shell. Ganymede is larger than Mercury and has its own magnetic field. Callisto is ancient, cratered, and deeply frozen. Saturn gives another example with Titan. Titan has a thick nitrogen atmosphere, methane clouds, methane rain, and lakes of liquid hydrocarbons near its poles. A giant planet around Alpha Centauri A could also have moons, although their existence remains unknown. If a large moon orbited within the habitable zone, the moon rather than the planet could become the more interesting place. A rocky moon with an atmosphere would receive light from Alpha Centauri A. It would also feel tides from the giant planet it orbits. Tides are gravitational stretching forces. On Earth, tides mostly move ocean water. On some moons, tides can flex the interior and create heat. That is what helps drive Io's volcanoes and may help keep Europa's ocean liquid. This possibility makes the candidate feel more complicated. The planet itself may be hostile by Earth standards. Its surroundings could still reveal where smaller, colder, warmer, rocky, icy, or hidden places might exist. A gas giant in the habitable zone would act like a marker. It would show that planet formation reached a serious scale around Alpha Centauri A. It would prove that the system can build large worlds despite the presence of a second nearby star. It would hint that smaller bodies may have formed nearby as well. The first visible object may simply be the easiest one to see. A giant planet glows more strongly in infrared than a small rocky world. Its size gives telescopes a better chance. A smaller Earth-like planet could sit deeper inside the glare, too faint for current instruments to separate from the star. So the possible gas giant does not close the mystery. It widens the search. Inside Alpha Centauri, the first world pulled from the light may only be the largest clue in a system where the smaller worlds are still waiting unseen. Then the possible planet did something that made the story even stranger. It disappeared. In August 2024, Webb observed Alpha Centauri A and found a faint source in the right kind of location. The signal looked consistent with a possible giant planet. It appeared near the region where a planet could orbit with temperatures that might allow liquid water under the right conditions. The object was dim, extremely dim, more than 10,000 times fainter than the star beside it. Still, after the glare was reduced and the data was processed, something remained. A faint point, a possible world, a candidate sitting inside the nearest sun-like system beyond our own. That alone would have been enough to make Alpha Centauri one of the most important targets in astronomy. Researchers returned to the system in February 2025. They looked again. The same object was gone. A second follow-up came in April 2025. The result was the same. No clear reappearance, no simple confirmation, no clean second image to settle the case. For an ordinary discovery, this would sound like failure. In planet hunting, it can mean something more delicate. A planet moves. A telescope sees only a slice of its orbit at a specific moment. If the object shifted closer to Alpha Centauri A from Webb's point of view, it could have slipped back into the bright inner glare of the star. The planet could still exist while becoming temporarily invisible. This is called orbital motion. Every planet moves around its star, and the shape of that path determines where it appears in the sky from Earth. Earth takes 1 year to orbit the Sun. Jupiter takes almost 12 years. A giant planet around Alpha Centauri A could take years to complete one orbit, depending on how far it sits from the star. During that slow movement, the angle between the planet, its star, and Earth changes. At one moment, the planet might appear far enough from the star for Webb to separate it. Months later, the same planet might appear closer to the star's edge, swallowed by the leftover glow. To test this, researchers modeled millions of possible orbits. Each orbit was a mathematical path the planet could be following. Some paths were circular, others were more stretched. Some placed the planet slightly closer to the star, others carried it farther out. The goal was to see whether a real planet could appear in August 2024, then hide during the February and April 2025 observations. Many possible paths allowed exactly that. The candidate could have moved into a position where Webb's coronagraph and instruments could no longer separate it from Alpha Centauri A. A coronagraph can block the star's brightest center, creating an artificial eclipse. Around that blocked region, a difficult zone remains. Astronomers sometimes call this the inner working angle. It is the closest distance from the star where the telescope can reliably detect a faint companion. Inside that zone, starlight still dominates. A real planet can vanish into the instrument's blind spot. That is why the phrase disappearing planet fits so well. The object did not have to physically vanish. It may have passed into a place where the star became too bright around it. For a system only 4.37 light-years away, that is unsettling. Alpha Centauri is close enough that its light reaches us in just over 4 years. Its stars are among the nearest targets ever studied by Webb. Yet even there, a possible planet can appear briefly, escape confirmation, and leave scientists building millions of orbital paths to explain where it went. The nearest Sun-like system becomes less like a solved map and more like a moving scene, a place where worlds may be present, shifting through glare, timing, and geometry. The discovery remains a candidate because science demands repeated evidence. A planet must be seen again. Its motion must match an orbit. Its brightness must make physical sense. Its signal must survive every ordinary explanation. Until then, the possible world around Alpha Centauri A stays suspended between detection and uncertainty. That uncertainty matters because it tells us something deeper about the system. If a giant planet can be this difficult to confirm beside the nearest Sun-like star, then smaller rocky planets would be even harder to find. The brightest clue may already be slipping in and out of view. The quieter worlds could still be buried deeper in the light. A giant planet is difficult to find beside Alpha Centauri A. A smaller rocky planet would be much harder. The reason comes down to size, heat, and light. A gas giant may be many times wider than Earth. Jupiter is about 88,000 miles across at its equator. Earth is about 7,900 miles across. That difference gives a giant planet a much larger surface area to reflect starlight or release infrared heat. A rocky planet closer to Earth's size gives telescopes far less to work with. Invisible light, an Earth-like world beside a Sun-like star, can be roughly 10 billion times fainter than the star itself. That is the kind of contrast that turns a planet into something almost erased by light. Even if the planet is there, the star fills the image with glare first. The telescope must remove the glare cleanly enough for a tiny leftover signal to remain. At Alpha Centauri, the challenge becomes even more delicate. The system is nearby, so its planets would appear slightly more separated from their stars than planets in distant systems. That helps. The same closeness also means Alpha Centauri A and B move noticeably across the sky, and their positions relative to each other keep changing through their 80-year orbit. A planet can move through parts of its orbit where it is easier to see, then pass into a region where the star's light overwhelms it. This is orbital timing. A world may only become visible during certain windows, when it appears far enough from its star from our point of view. If astronomers look too early, the planet may be buried beside the star. If they look too late, it may have moved back into the glare. That makes Alpha Centauri feel like a scene where the hidden objects are constantly shifting. The stars are moving. Any planets are moving. Earth and Webb are moving as they observe. The whole search depends on matching the right instrument to the right moment. Alpha Centauri. B has its own history of difficult planet claims. In 2012, astronomers announced a possible Earth-mass planet around Alpha Centauri b. The signal came from tiny changes in the star's motion. That method is called radial velocity. It works by measuring how a star shifts slightly toward and away from Earth as a planet's gravity tugs on it. The movement can be extremely small. For an Earth-sized planet around a Sun-like star, the star may wobble by less than a mile per hour. That is walking speed measured across a distance of more than 25 trillion miles. The 2012 Alpha Centauri b candidate would have orbited extremely close to the star, with a year only a few days long. Later studies questioned the signal. The possible planet faded into uncertainty as researchers reanalyzed the data and found that stellar activity and sampling patterns could imitate a planet. That episode matters because it shows how hard this system is. Even the nearest Sun-like stars can produce signals that look planetary, then become doubtful under closer examination. Stars have surfaces that churn. Dark star spots rotate in and out of view. Magnetic activity changes the shape of spectral lines, the tiny color fingerprints astronomers use to measure motion. A planet signal has to stand out from all of that. Small worlds around Alpha Centauri. A or B could still be hiding in the data. They may be too faint to image directly. They may have orbits that keep them close to the glare during our best observing windows. They may tug on their stars so gently that years of measurements are needed before the pattern becomes clear. This is why the nearest stellar system can remain incomplete. Astronomy has already found thousands of exoplanets across the galaxy. Many were found by the Kepler Space Telescope, which watched stars dim as planets crossed in front of them. Others were found by measuring the wobble of their stars. Those techniques work beautifully in many systems. Alpha Centauri asks for something even harder. It asks us to find the smallest worlds around the brightest nearby stars, in a binary system where stellar motion and starlight constantly complicate the view. Our instruments are only now reaching the edge of that task. The possible giant around Alpha Centauri A may be the first large shape emerging from the glare. Smaller rocky worlds could still be present, silent and unresolved, waiting for sharper telescopes or a more fortunate moment in their orbit. Yet the Alpha Centauri system already has one confirmed planetary neighborhood. It sits around the faint outer star, Proxima Centauri, where the search moves away from the bright central pair and into a colder, redder, more dangerous part of the system. The confirmed planetary neighborhood in Alpha Centauri belongs to the smallest star in the system, Proxima Centauri, a faint red dwarf on the outer edge of the system. This star is too dim to see with the unaided eye from Earth. Even though it is the closest known star to the Sun, its visible light is weak enough that it hides from ordinary human sight. Its importance changed in 2016. That year, astronomers announced the discovery of a planet orbiting Proxima Centauri. The planet was named Proxima Centauri b. It became the closest confirmed exoplanet to Earth. An exoplanet simply means a planet outside our solar system. Before the 1990s, no planet had been confirmed around a normal star like the Sun. Now thousands are known. Some are larger than Jupiter. Some orbit so close to their stars that their surfaces may be molten. Some are small rocky worlds only a little larger than Earth. Proxima Centauri b became different from all of them because of its address. It orbits the nearest star. The discovery did not come from a photograph. Astronomers found it through the radial velocity method. That method looks for tiny shifts in a star's motion as a planet pulls on it with gravity. The planet and star both orbit a shared center of mass. The star's motion is much smaller because the star is far more massive. Still, sensitive instruments can detect that motion as a shift in the star's light. When the star moves slightly toward Earth, its light shifts a little bluer. When the star moves slightly away, its light shifts a little redder. This is called the Doppler effect. It is the same basic effect that makes an ambulance siren sound higher as it approaches and lower as it moves away. In Proxima's light, astronomers found a repeating signal. A planet was tugging on the star every 11.2 days. That gave Proxima b one of its most important measurements. A year on Proxima b lasts only 11.2 Earth days. Its orbital distance is about 0.048 astronomical units. 1 astronomical unit is the average distance from Earth to the Sun, about 93 million miles. Proxima b orbits at less than 5% of that distance. In our solar system, that would place a planet far inside Mercury's orbit. Mercury orbits the Sun at about 0.39 astronomical units. Proxima b sits more than 8 times closer to its star than Mercury sits to ours. Around a star like the Sun, that would be a furnace. Around Proxima Centauri, the situation changes because the star is so small and dim. Proxima has only about 12% of the Sun's mass. Its light output is tiny compared with the Sun's. A planet has to orbit extremely close to receive enough warmth. That is why Proxima b can sit so near its star and still land in the region scientists call the habitable zone. The habitable zone is the range of distances where a planet could receive the right amount of starlight for liquid water on its surface, assuming it has a suitable atmosphere. That last part matters. The habitable zone only describes incoming energy from the star. It does not guarantee oceans. It does not guarantee air. It does not guarantee a gentle surface. Venus sits near the inner edge of the Sun's habitable zone region, yet its surface is hot enough to melt lead. Mars sits near the outer edge, yet most of its water is frozen or lost. A planet's atmosphere, magnetic field, chemistry, rotation, and history all matter. Proxima b is estimated to be roughly Earth mass. That makes it especially tempting. A world with about Earth's mass could be rocky. It could have gravity strong enough to hold gases. It could have formed with minerals, metals, and possibly water-bearing material. From a distance, those facts sound like the beginning of a second Earth story. Nearest star, Earth-sized planet, possible habitable zone. Those details are enough to make Proxima b one of the most studied worlds outside the solar system. The measurements also begin to tighten around it. An 11.2-day orbit means the planet lives extremely close to its star. That closeness brings warmth from a dim red dwarf. It also places the planet deep inside the star's magnetic environment. The nearest known world beyond the solar system may sit in the right temperature region, while moving through conditions far harsher than the phrase habitable zone first suggests. Proxima b sounds Earth-like only from a great distance. Its mass may be close to Earth's. Its orbit may place it inside the temperature region where liquid water could exist. Its star is the closest known star to the Sun. Those facts make the planet feel familiar. Then the numbers begin to change the picture. Earth takes 365 days to travel once around the Sun. That yearly rhythm shapes almost everything we know. Seasons, agriculture, migration, calendars. Human history has been built around that slow orbit. Proxima b completes its year in only 11.2 Earth days. A person standing there, if standing were possible, would pass through more than 30 local years during one Earth year. A child born on Proxima b would be over 1,000 local years old before reaching the age of 30 on Earth. The planet moves that quickly because it orbits very close to its star. Its average distance from Proxima Centauri is about 0.048 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. So Proxima b orbits at roughly 4.5 million miles from its star. That is less than 5% of Earth's distance from the Sun. Mercury, the innermost planet in our solar system, orbits at about 36 million miles from the Sun. Proxima b circles more than 7 times closer to its star than Mercury circles ours. Around a star like the Sun, that distance would be devastating. A world there would be scorched by sunlight. Rock could heat until the surface became hostile to almost any chemistry we associate with life. Proxima Centauri changes the calculation because it is small and dim. It has about 12% of the Sun's mass. Its visible glow is faint enough that even from Earth's nearest neighboring star, human eyes need a telescope to see it. A planet has to huddle close to receive meaningful warmth. That closeness may give Proxima b only about 2/3 of the starlight Earth receives from the Sun, depending on the exact measurements used. From a pure energy standpoint, the orbit can make sense. The planet sits close because the star is weak. The problem is that warmth is only one part of habitability. Distance also controls exposure. Earth orbits far enough from the Sun that our planet experiences its star from a relatively protected separation. Solar storms still reach us. Charged particles still strike Earth's magnetic field. Ultraviolet radiation still shapes the upper atmosphere. Even so, 93 million miles gives our planet space. Proxima b lives in a much tighter environment. At 4.5 million miles, the star would dominate the sky. Its gravity would pull strongly on the planet. Its magnetic activity would happen nearby, with far less distance for radiation and charged particles to spread out before reaching the world. A flare from Proxima Centauri would matter in a direct and intimate way. A flare is a sudden release of magnetic energy from a star's surface. On the Sun, powerful flares can disturb radio communication, damage satellites, and create auroras near Earth's poles. Around Proxima b, similar events would arrive from a star dozens of times closer than the Sun is to Earth. Even if Proxima is dim in ordinary light, its activity can still be intense. That creates the harsher side of the 11-day orbit. The same closeness that places the planet in the habitable zone also places it deep inside the star's reach. The orbit gives Proxima b warmth. It also gives the star more power over the planet's air, surface, and long-term history. So the nearest known world beyond our solar system becomes a strange balance. It may sit where temperatures could allow water. It also circles a red dwarf so closely that every burst from the star becomes part of the planet's environment. That danger begins with Proxima itself, because small stars can sometimes behave with surprising violence. Proxima Centauri belongs to the most common family of stars in the galaxy. Red dwarfs make up roughly 3/4 of all stars in the Milky Way. They are small, cool, and extremely long-lived. Some may shine for hundreds of billions of years. The smallest ones may last for trillions of years, far longer than the current age of the universe. That long lifetime makes them tempting places to search for planets. A world around a red dwarf could, in theory, have an enormous amount of time for chemistry to unfold. Proxima Centauri has that kind of longevity. Its surface temperature is around 3,000 degrees Kelvin, much cooler than the Sun's surface, which is about 5,800 degrees Kelvin. Its ordinary visible light is faint. From a distance, it seems quiet. Up close, the star is far more active than its dim glow suggests. Proxima Centauri is a flare star. That means magnetic energy can build up in its outer layers, then release suddenly. A stellar flare happens when tangled magnetic field lines snap into a new arrangement. The process throws energy into space as ultraviolet light, X-rays, and streams of charged particles. Charged particles are tiny pieces of atoms, mostly protons and electrons, moving at high speed. On Earth, powerful solar flares can disturb satellites, radio signals, and power systems. Our atmosphere and magnetic field absorb much of the damage. Proxima b orbits much closer to its star than Earth does to the Sun. That closeness changes the danger. The same flare that might be manageable at Earth's distance becomes more severe when the planet is only about 4.5 million miles away. Radiation spreads out as it travels. At a shorter distance, more of it reaches the planet. In 2016, the same year Proxima b was announced, scientists were already examining whether the planet could endure this environment. Follow-up studies found that Proxima produces frequent smaller flares and occasional powerful events. In March 2017, telescopes detected a major flare from Proxima Centauri that briefly made the star much brighter at millimeter wavelengths, a form of light used by radio observatories to study cold dust and energetic activity. For a planet orbiting nearby, events like that matter over long spans of time. One flare may last minutes or hours. A planetary atmosphere has to survive millions and billions of years of repeated exposure. Ultraviolet radiation can break apart water vapor and other molecules high in the atmosphere. X-rays can heat the upper layers of air, making gases easier to lose into space. Charged particles can slam into atmospheric molecules, stripping electrons away and driving chemical reactions. Around Earth, the magnetic field helps guide many charged particles toward the poles, where they create auroras. Around a planet with a weak magnetic field, or no magnetic field, those particles can strike the atmosphere more broadly. Mars gives a nearby example. It once had liquid water on its surface. River valleys, lake beds, and minerals formed in water still mark the planet today. Over time, Mars lost much of its atmosphere. Its low gravity and weak global magnetic protection made it vulnerable to solar wind, the stream of particles flowing from the Sun. Proxima b faces a more intense version of that basic problem. Its star is dimmer in visible light, yet its close orbit places it deep inside the region where stellar activity matters. A red dwarf can provide enough warmth for liquid water, while also exposing a planet to radiation conditions that reshape its surface environment. That is why Proxima b remains so difficult to judge. The planet may have formed with water. It may have formed with air. It may have begun with ingredients that sound promising from Earth. The star beside it has had billions of years to test those ingredients. Habitability around Proxima depends on endurance. A world has to keep enough atmosphere to hold pressure at the surface. It has to preserve enough shielding for complex chemistry. It has to survive a star that can turn magnetic tension into sudden bursts of radiation. The nearest confirmed world beyond our solar system may still be there, circling every 11.2 days. The deeper issue is whether anything protective remains wrapped around it. For Proxima b, the most important layer may be one we have never seen: its atmosphere. An atmosphere is a planet's envelope of gas. On Earth, that envelope reaches hundreds of miles upward, but most of its mass is packed close to the ground. At sea level, Earth's air presses down with about 1 bar of pressure. That pressure matters because liquid water needs more than the right temperature. It also needs enough pressure to remain liquid on the surface. With too little air above it, water boils away or freezes more easily. Mars shows this clearly. Its average surface pressure is less than 1% of Earth's. Because the air is so thin, liquid water struggles to remain stable on the Martian surface today. Earth's atmosphere also spreads heat. The equator receives more sunlight than the poles. Winds and oceans move some of that energy around the planet. Carbon dioxide, water vapor, and methane absorb infrared heat, helping keep the surface warmer than bare rock would be. This warming effect is called the greenhouse effect. On Earth, it raises the average surface temperature from far below freezing to about 59 degrees Fahrenheit. The same kind of layer would be crucial for Proxima b. A thick enough atmosphere could move heat away from the star-facing side. It could soften temperature extremes. It could shield the surface from ultraviolet radiation. It could allow clouds, weather, and perhaps liquid water under the right conditions. The problem is keeping that atmosphere. Proxima b orbits only about 4.5 million miles from its star. That closeness exposes it to Proxima Centauri's stellar wind. Stellar wind is a stream of charged particles flowing outward from a star. The Sun has one. It flows past Earth at hundreds of kilometers per second. Earth is protected by a global magnetic field created by moving liquid iron in the outer core. That magnetic field carves out a protective bubble in space called the magnetosphere. It redirects many charged particles around the planet before they can directly strike the atmosphere. Proxima b may have a magnetic field. The current evidence cannot tell us. Even if it does, the planet's close orbit may place it under stronger pressure from stellar wind than Earth experiences. Over millions of years, charged particles can erode the upper atmosphere. They can knock molecules into space. They can heat the highest layers of gas until some particles move fast enough to escape the planet's gravity. Ultraviolet radiation adds another pathway. High-energy light can split water vapor apart. Hydrogen is especially light, so it can escape into space more easily than heavier gases. If enough water vapor reaches the upper atmosphere, a planet can slowly lose water over long periods. This process has shaped worlds in our own solar system. Venus may once have had far more water than it has today. Mars once had rivers, lake beds, and minerals formed in wet environments. Both planets show how atmosphere and water can change across billions of years. Proxima b may have started with a thick blanket of gas. That blanket could still be there, changed but present. A dense atmosphere rich in carbon dioxide might trap heat and move it around the planet. A thinner atmosphere might leave the surface more exposed. A mostly stripped atmosphere would turn the planet into something closer to an airless rock, warmed on one side and frozen on the other. There is also the possibility that Proxima b struggled from the beginning. Red dwarfs spend a long, early phase shining with stronger high-energy radiation relative to their later lives. A planet that now sits in the habitable zone may have endured a harsher youth while its star was more active. During that early era, water could have been broken apart. atmospheric gases could have escaped. The surface could have been altered before the planet ever settled into its present orbit. That is why Proxima b remains a gamble. Its mass and orbit make it one of the most tempting nearby worlds. Its star makes every hopeful detail conditional. Atmosphere becomes the difference between a planet with weather and a planet with exposed stone, between possible oceans and a dry surface, between a world that stores heat and a world that loses it into space. Even with some air still wrapped around it, Proxima b may have no true Earth comparison. The next possibility is even stranger. A planet can keep an atmosphere and still live with one side turned forever toward its star. A surviving atmosphere would only solve part of Proxima b's problem. The planet also has to deal with gravity from extremely close range. At about 4.5 million miles from its star, Proxima b is close enough for tidal forces to matter. A tide is created when gravity pulls more strongly on the near side of an object than the far side. On Earth, the Moon's gravity raises tides in the oceans. The Sun does the same, though from much farther away. On a close orbiting planet, tides can reach deeper than water. They can stretch the solid body of the planet itself. Over long spans of time, that stretching creates friction inside the planet. Friction turns motion into heat. It also changes the planet's rotation. A world that begins by spinning freely can slowly lose that spin until one side always faces its star. This state is called tidal locking. The Moon gives the familiar example. The Moon rotates once in the same amount of time it takes to orbit Earth. That is why we always see the same lunar face from the ground. The far side exists, but it points away from Earth. Proxima b may be locked in the same kind of relationship with Proxima Centauri. Its orbit lasts 11.2 days. If the planet is tidally locked, its rotation would also last 11.2 days. That means one hemisphere would face the star continuously. The other hemisphere would face away into space. On the star-facing side, Proxima Centauri would hang in almost the same place in the sky. Near the center of that hemisphere, the star could remain overhead without rising or setting. This point is called the substellar point. It is the place on a locked planet where the star appears highest. Heat would pour onto that region again and again. The landscape there, if exposed, could experience endless daylight. Clouds might gather if water evaporated strongly. Winds might flow outward as warm air rose and moved away from the heated center. On the opposite hemisphere, the sky would remain dark. No sunrise would cross the horizon. No daily cycle would warm the surface. Any exposed water could freeze. Gases in the atmosphere could become colder and denser. In extreme cases, some gases might even freeze out onto the night side if the atmosphere were too thin to move heat around. Between these two halves lies the terminator. The terminator is the boundary between day and night. On Earth, the terminator sweeps across the planet every 24 hours as sunrise and sunset move around the globe. On a locked planet, the terminator could stay nearly fixed. It would form a permanent twilight ring around the world. There, the star would sit low near the horizon. Temperatures might be less extreme than the hot center of the day side or the frozen depth of the night side. This is why the terminator becomes so important in models of Proxima b. If the planet has a thick enough atmosphere, winds could carry heat from the day side into the dark hemisphere. If it has oceans, currents could also move warmth around the globe. A planet with air and water might avoid the sharpest extremes. A planet with a thin atmosphere could become divided into brutal zones. A bright, heated face. A dark, frozen face. A narrow region where conditions might remain stable. That would make Proxima b profoundly different from Earth. Earth spins once every 24 hours. Most places experience morning, afternoon, evening, and night. Weather systems move through changing sunlight. Seasons shift as the planet orbits the Sun with a tilted axis. A locked Proxima b would have a more permanent geography of light. Climate would depend less on day and night cycles and more on location. Distance from the substellar point could matter as much as latitude matters on Earth. The nearest confirmed planet beyond the solar system may therefore have a kind of habitability built around edges. The useful places may be limited. The stable climates may be local. The safest regions may exist where light arrives gently, where air can move heat, and where the surface avoids both constant heating and permanent darkness. That turns Proxima b into a much narrower possibility. A world where survival, if it exists at all, may depend on the thin middle between two extremes. The thin middle of Proxima b is where the most fragile possibility begins. A tidally locked planet does not offer habitability evenly across its surface. The star-facing side may receive constant light. The dark side may lose heat into space for billions of years. Between them, the terminator could form a permanent twilight zone, a ring of low-angle starlight around the planet. There, Proxima Centauri would sit near the horizon. Shadows could stretch for enormous distances. Temperatures might stay more stable than the heated center of the day side or the frozen depth of the night side. This is one of the places scientists imagine liquid water might survive, assuming the planet has enough atmosphere to move heat around. A thick atmosphere could carry warmth into colder regions. Winds could flow from the day side toward the night side and return at different altitudes. On Earth, winds help move tropical heat toward the poles. On Proxima b, winds might decide whether the night side becomes a frozen trap or part of a circulating climate. Oceans would matter as well. Water holds heat more effectively than rock or air. A deep ocean near the terminator could absorb energy during long exposure to dim red light, then distribute that warmth through currents. Earth's oceans already do this. The Gulf Stream carries warm water from the tropics toward the North Atlantic, helping shape the climate of Western Europe. A locked world around Proxima would need its own version of heat transport, likely stranger and more permanent. Surface life would still face radiation. Proxima Centauri's flares can release ultraviolet light and charged particles. Ultraviolet light can damage complex molecules, including DNA on Earth. Charged particles can break chemical bonds and alter atmospheric chemistry. Any life near the surface would need shielding. On Earth, ozone absorbs much of the sun's harmful ultraviolet radiation. Water also protects living things. Just a few meters below the surface of an ocean, ultraviolet light is greatly reduced. Rock offers even stronger protection. Microbes on Earth live deep underground, inside cracks in stone, using chemical energy from minerals rather than sunlight. In South African gold mines, bacteria have been found more than 2 miles below the surface, surviving in hot, dark water trapped in rock. Near hydrothermal vents on Earth's ocean floor, entire ecosystems live without sunlight. Tube worms, clams, shrimp, and bacteria gather around vents where heated, mineral-rich water pours from the crust. The foundation of those ecosystems is chemosynthesis. That means life uses chemical reactions for energy instead of photosynthesis. Photosynthesis uses light. Chemosynthesis uses materials like hydrogen sulfide or methane. A planet like Proxima b may need that kind of hidden strategy. Life could shelter under ice. Life could exist below an ocean surface. Microbial communities could live in pores of rock, protected from radiation by meters of material overhead. Even the night side might hold possibilities if internal heat, volcanic activity, or a subsurface ocean kept some water liquid below the frozen exterior. The icy moons in our own solar system show why that idea matters. Europa, orbiting Jupiter, likely has a global ocean beneath its ice shell. Enceladus, a small moon of Saturn, sprays water vapor and ice grains into space from cracks near its south pole. Those worlds receive little sunlight compared with Earth. Their possible habitability comes from hidden oceans and internal energy. Proxima b could be different in almost every detail, yet the lesson is useful. A world can look hostile from above, while keeping its most important environments out of sight. That makes the closest possible alien biosphere especially difficult to imagine. A biosphere means the total living system of a world, from microbes to larger organisms if they exist. On Earth, the biosphere announces itself through forests, oceans, oxygen, seasonal color, and the chemistry of the atmosphere. On Proxima b, the most protected living regions could be buried, dark, underwater, or confined near the twilight boundary. A telescope would see none of that directly. It would receive only light from the planet and star. Tiny hints in color, tiny hints in heat, tiny hints in the gases above the surface. So the search begins to shift. Reaching Proxima b physically remains far beyond anything humanity can do right now. Understanding whether it is alive may depend on learning to read a hidden world from 4.24 light-years away. To study Proxima b, scientists have to treat light like evidence. A telescope cannot scoop air from a planet 4.24 light-years away. It cannot lower an instrument through the clouds. It cannot listen to wind, taste minerals, or watch waves move across a surface. It receives photons, tiny packets of light that have crossed more than 25 trillion miles. Those photons may carry the only clues we can get. Astronomers study planets in several ways. They can measure orbital motion. They can watch how a star wobbles as a planet pulls on it. They can look for changes in brightness as a planet moves around its star. They can search for heat, especially in infrared light, where warm objects glow. They can also study atmospheres through spectroscopy. Spectroscopy means spreading light into its colors and looking for missing pieces. Every gas absorbs certain wavelengths of light. Water vapor leaves one pattern. Carbon dioxide leaves another. Methane, oxygen, ozone, and nitrogen-bearing gases each leave their own fingerprints. On Earth, sunlight passes through the atmosphere, bounces from clouds, land, and ocean, then travels into space with chemical clues inside it. If a distant civilization had a powerful enough telescope, Earth's light could tell them that our atmosphere contains oxygen, water vapor, carbon dioxide, and methane. That combination would be interesting because oxygen and methane react with each other over time. Their long-term coexistence suggests some process keeps refreshing them. On Earth, that process is life. Plants, algae, and cyanobacteria help maintain oxygen through photosynthesis. Microbes, wetlands, livestock, and geological processes contribute methane. A biosignature is a possible sign of life in a planet's atmosphere or surface. It is never a simple label. A gas can have living and non-living sources. Volcanoes can release gases. Sunlight can drive chemical reactions. Water can interact with rock. A strong biosignature needs context. The planet's star, temperature, orbit, size, and atmosphere all matter. Proxima b would be one of the most tempting places to try this because it is so close. A planet 20 light-years away sends us a much weaker signal. A planet 100 light-years away becomes harder again. Light spreads out as it travels, so distance makes every measurement fainter. Proxima b has the advantage of being nearby. Its star is small, which may also help in some ways. A small star has less surface area than a Sun-like star, so a planet can block or affect a larger fraction of its light if the geometry lines up. Around red dwarfs, atmospheric signals can sometimes be easier to detect than around larger stars. The same star that makes Proxima b dangerous may also make it scientifically valuable. Still, this search remains extremely difficult. Proxima b has never been seen as a clear, separate world. Its existence is known from the tiny motion it causes in its star. To study its atmosphere, astronomers would need the right observing method, the right telescope, and enough separation from Proxima's own activity. That last part is severe. Proxima Centauri flares. Its brightness changes. Its magnetic activity can alter the very light astronomers need to measure. A flare can add ultraviolet and X-ray radiation. Star spots can rotate across the surface. Hot and cool regions can change the star's spectrum. Those effects can imitate, hide, or distort the signal from a planet's atmosphere. A small, rocky planet gives only a very thin clue. If Proxima b has air, the atmosphere would be a narrow ring around the planet from our viewpoint. The signal might be only a few parts per million in the star's light. That means scientists may need many observations, careful filtering, and future telescopes built specifically for nearby Earth-sized worlds. This is the strange future of Alpha Centauri. Before any probe reaches it, telescopes may already begin turning its planets into partial worlds. Measured worlds, modeled worlds, worlds known through temperature, orbit, brightness, and chemistry. That knowledge would be powerful. It would also be incomplete. We may learn whether Proxima b has air before we ever see its surface. We may detect water vapor, carbon dioxide, or methane without knowing where those gases came from. Alpha Centauri may become clearer from Earth while remaining physically untouched across the enormous dark between stars. Alpha Centauri becomes even stranger when measured against the farthest machines humanity has ever sent. Voyager 1 launched from Cape Canaveral on September 5, 1977. Voyager 2 launched a little earlier, on August 20, 1977. Both spacecraft were built for a planetary mission. Their original task was to visit the giant planets, Jupiter, Saturn, and for Voyager 2, Uranus and Neptune. The mission depended on a rare alignment of the outer planets that happens about once every 176 years. Engineers use gravity assists to steal tiny amounts of orbital energy from planets, bending the spacecraft paths and increasing their speed. A gravity assist works like a slingshot. The spacecraft falls toward a moving planet, swings around it, and leaves with a new direction and more speed relative to the Sun. Voyager 1 passed Jupiter in March 1979. It reached Saturn in November 1980. After its Saturn encounter, the spacecraft was flung upward out of the plane where most planets orbit. From there, it began moving toward the edge of the Sun's protective bubble. That bubble is called the heliosphere. The heliosphere is created by the solar wind, a stream of charged particles flowing outward from the Sun. Far away, this stream meets the thin gas and magnetic field between stars. The boundary is called the heliopause. Voyager 1 crossed that boundary on August 25, 2012. Voyager 2 crossed it on November 5, 2018. That means both spacecraft have entered interstellar space. They are traveling through the environment between stars, where the Sun's direct particle flow has given way to the surrounding galaxy. This sounds enormous because it is enormous. Voyager 1 is now more than 15 billion miles from Earth. A radio signal from the spacecraft takes more than 22 hours to reach us. Every command sent from Earth requires nearly a full day to arrive. Every reply takes nearly a full day to return. A simple exchange with the spacecraft stretches across almost 2 days, and still, Voyager 1 has barely begun the distance to the nearest stars. Alpha Centauri is more than 25 trillion miles away. Voyager 1 has traveled for nearly half a century and has covered only a tiny fraction of that gap. At its current speed, a Voyager-like spacecraft would need tens of thousands of years to cover the distance to the Alpha Centauri system. That is longer than recorded human history, longer than agriculture has existed, longer than the entire span from the last ice age to the modern world. The spacecraft itself also shows the limits of sending machines into deep time. Voyager 1 and Voyager 2 run on radioisotope thermoelectric generators. These generators use heat from decaying plutonium-238 to make electricity. At launch, each spacecraft had enough power to run its instruments, heaters, computers, and transmitter. Plutonium-238 loses energy slowly, with a half-life of about 87.7 years. As the power declines, engineers have to make careful choices. Some instruments have already been turned off. The cameras stopped being useful decades ago, after the planetary flybys ended. Other systems have been shut down to save electricity and heat. The spacecraft are still alive only because engineers keep managing their dwindling power with extraordinary care. Voyager 1 is the most distant human-made object in existence. Voyager 2 is the only spacecraft ever to visit Uranus and Neptune. Both have crossed into the space between stars. Yet neither is heading for Alpha Centauri. Neither could slow down near another star. Neither will send pictures of another planetary system. Eventually, their transmitters will fall silent. After that, they will keep drifting as cold metal artifacts from the 1970s. They will carry human work into the dark, while the nearest star system remains far beyond their reach. That is the scale hidden inside the word nearby. Alpha Centauri is close enough for telescopes to study its stars and planets. It is distant enough to make our greatest spacecraft look almost motionless. Reaching it requires more than patience. It requires a new kind of journey, built around speeds far beyond anything Voyager ever achieved. A true journey to Alpha Centauri needs speed on a scale Voyager never approached. Voyager 1 moves at about 17 kilometers per second relative to the Sun. Light moves at about 300,000 kilometers per second. That means Voyager travels at only a tiny fraction of light speed. A spacecraft headed to Alpha Centauri with that kind of velocity would need tens of thousands of years. This is why scientists and engineers have imagined a different kind of mission. A tiny probe, a reflective sail, a powerful laser. The most famous version is Breakthrough Starshot, announced in 2016. The idea is to build gram-scale spacecraft, each one small enough to fit on a chip. Attached to each tiny craft would be an extremely thin light sail. A large laser array, either on Earth or in space, would fire a concentrated beam at the sail. Light has momentum. Each photon carries a tiny push. With ordinary sunlight, that push is gentle. With an enormous laser focused on an ultralight sail, the push could become powerful enough to accelerate a tiny spacecraft to a significant fraction of light speed. Some versions of the concept imagine speeds near 20% of light speed. At that velocity, a probe could cross the distance to Alpha Centauri in roughly 20 years. That changes the emotional scale of the mission. A trip that would take Voyager tens of thousands of years becomes short enough for the same generation that launched it to receive the first data. The signal would still need more than 4 years to travel back to Earth. Even so, the mission would become something almost imaginable. A launch in 1 decade, a flyby a few decades later. Images and measurements arriving after the spacecraft had already passed through the system. That last detail is where the promise begins to narrow. A laser-driven microprobe would be moving incredibly fast. At 20% of light speed, it would travel about 60,000 kilometers every second. That is fast enough to cross the distance from Earth to the Moon in about 6 seconds. It could cross 1 astronomical unit, the distance from Earth to the Sun, in about 42 minutes. A spacecraft moving that quickly through Alpha Centauri would have very little time to observe anything closely. The central stars, possible planets, dust, magnetic fields, any small world near Proxima or Alpha Centauri A. All of it would sweep past at a speed no human mission has ever attempted. The probe might gather images for hours or days, depending on its path and target. Then it would continue into deeper space. There would be no orbit insertion. There would be no long survey. There would be no second pass. Stopping is the part that makes interstellar travel so punishing. To reach Alpha Centauri quickly, a craft must gain enormous kinetic energy. Kinetic energy is the energy of motion. The faster something moves, the more energy it carries. Increase speed by 10 times, and the kinetic energy rises by 100 times. A probe moving at a fraction of light speed cannot simply arrive and slow down like an airplane approaching a runway. Space has no air to brake against. A chemical rocket would need fuel. Carrying fuel adds mass. Extra mass requires more energy to accelerate. Then even more fuel is needed to slow down at the end. This is the trap built into rocket travel. A laser can push a sail from Earth, but that same laser cannot easily pull the probe backward once it reaches Alpha Centauri. Researchers have suggested other braking ideas. A magnetic sail could interact with charged particles from the destination star. A light sail could use radiation from the star itself. A larger mission could carry propulsion for deceleration. Each option adds difficulty, mass, uncertainty, or time. For a gram-scale probe, the simplest version is a flyby. Fast, brief, unrecoverable. That may still be revolutionary. A successful flyby could measure the environment around another star. It could photograph a planet as more than a point. It could reveal dust, radiation, magnetic fields, and perhaps the rough brightness of hidden worlds. Humanity would receive real data from the nearest star system for the first time. Yet the mission would also show how distant Alpha Centauri remains. The first spacecraft to reach it may arrive like a spark passing through a dark room, bright for a moment, gone before it can stay. Even success may give us only a glimpse, leaving the nearest system partly seen and still untouched. A flyby would change history. It would give humanity its first direct measurements from another star system. Yet even that success would still leave Alpha Centauri mostly untouched. The probe would pass through. The system would remain. That is the strange position Alpha Centauri occupies. It is close enough to become a serious scientific target from Earth. Its light reaches us in a little over 4 years. Its 2 bright central stars can be measured again and again. Proxima Centauri b is close enough that future telescopes may study its atmosphere more carefully than planets dozens of light years away. The possible planet around Alpha Centauri A, if confirmed, would sit around the nearest sun-like star beyond our own. In the language of astronomy, this is an intimate distance. In the language of travel, it is still almost unreachable. Human presence there would require technology far beyond Voyager, far beyond chemical rockets, far beyond anything currently sitting on a launch pad. A crewed mission would be even harder than a robotic one. A spacecraft carrying humans would need shielding against radiation and interstellar dust. It would need life support that could run for decades or centuries. It would need food, water recycling, medical systems, spare parts, power, and enough protection to keep people alive across 25 trillion miles. Even a robotic orbiter would face the braking problem. It would need to arrive with enough speed to cross interstellar space in a meaningful time, then somehow lose that speed near Alpha Centauri. That is why the system may become known from a distance long before anything settles inside it. This is already how modern astronomy works. Scientists can map a planet's orbit without seeing its surface. They can estimate a world's mass by watching the star wobble. They can estimate size when a planet passes in front of its star and blocks a tiny amount of light. They can measure heat in infrared. They can use climate models to test whether a planet with a certain atmosphere might hold liquid water. For Proxima b, models can explore many possible versions of the same world. A thick carbon dioxide atmosphere, a thinner atmosphere with poor heat transport, a tidally locked climate with warm air moving from the dayside into the dark hemisphere, an ocean world with currents spreading heat around the planet, a dry rocky planet with almost no air left. Each version can be tested with physics. None can be confirmed by standing there. Biosignatures would make the distance feel even more haunting. A biosignature is a possible sign of life, such as oxygen, methane, water vapor, or other gases appearing in a meaningful combination. Future telescopes may search nearby planets for those chemical fingerprints. A signal from Alpha Centauri would be one of the most important discoveries in human history. Even then, the interpretation would be careful. Oxygen can build up through some non-living processes. Methane can come from biology or geology. Water vapor can suggest conditions while still leaving the surface unknown. A telescope might tell us that a planet has air. It might suggest clouds. It might reveal heat differences between day and night. It might even hint at chemistry that deserves serious attention. The planet itself would remain a distant point. No shoreline would be visible. No mountain range would be resolved. No living thing, if any existed, would be seen directly. Alpha Centauri becomes a halfway place between knowledge and absence. Close enough for data, distant enough for mystery. We may build maps from light. We may build climates from equations. We may build entire possible worlds from the faintest measurements a telescope can gather. That is the uneasy beauty of the nearest star system. It may become one of the best-known planetary environments beyond the solar system, while staying beyond human touch for centuries. The title begins to mean something deeper here. What scientists are finding inside Alpha Centauri is larger than a single possible planet. It is a layered system of bright stars, hidden worlds, uncertain atmospheres, and distances that keep every answer incomplete. So what is really inside Alpha Centauri? The answer is stranger than the simple phrase nearest star system suggests. At the center are Alpha Centauri A and Alpha Centauri B, two bright stars orbiting each other every 80 years. One is a little larger and brighter than the Sun. The other is a little smaller, cooler, and more orange. Together, they form the closest Sun-like pair to Earth. Farther out sits Proxima Centauri, a red dwarf with only about 12% of the Sun's mass. Faint enough to hide from the unaided eye, important enough to host the closest confirmed exoplanet we know. Proxima b circles that small star every 11.2 days. Its orbit is only about 0.048 astronomical units from Proxima, less than 5% of Earth's distance from the Sun. On paper, it sits in the habitable zone. In reality, it lives close to a flare star. That one sentence contains much of the Alpha Centauri problem. Hope and danger occupy the same place. A nearby planet may receive enough warmth for liquid water under the right conditions. That same planet may also endure ultraviolet bursts, charged particles, atmospheric erosion, and a permanent dayside if it is tidally locked. The habitable zone becomes a beginning rather than an answer, a location on a map, a place where deeper questions start. How much atmosphere remains? How much water survived the star's violent youth? How often do flares strike the planet? Can winds move heat from the bright side into the dark side? Could anything live underground, below ice, or underwater where radiation cannot easily reach? Alpha Centauri A now adds another layer. Webb may have found evidence of a possible giant planet near the closest Sun-like star beyond our own. That candidate appeared in August 2024. Then follow-up observations in February and April 2025 failed to recover it clearly. Researchers had to model millions of possible orbital paths to understand how a real planet could slip back into the star's glare. Even a possible gas giant, much larger than Earth, could become difficult to confirm in the nearest Sun-like system. A smaller rocky world would be quieter still. It could hide inside the leftover light of Alpha Centauri A. It could move through an orbit that only reveals it during narrow observing windows. It could tug on its star so gently that years of measurements are needed before the pattern becomes undeniable. That is what the system keeps teaching us. Closeness helps. Closeness also raises the standard. Because Alpha Centauri is nearby, every uncertainty feels sharper. A faint object around a star hundreds of light years away can remain a distant curiosity. A faint object around Alpha Centauri becomes part of our immediate cosmic neighborhood. It becomes something future telescopes will return to, something future missions may aim at, something that could become the first detailed planetary system beyond our own. Inside Alpha Centauri, there may be large worlds. There may be small rocky worlds. There may be moons around giant planets. There may be dead surfaces, stripped atmospheres, frozen night sides, hidden oceans, or chemistry we have no direct example for. the system contains 2 familiar-looking stars and 1 dangerous little red star. It contains 1 confirmed nearby world, and at least 1 possible object still suspended between detection and uncertainty. It contains places where liquid water might exist, and environments that could destroy the conditions water needs. That is why Alpha Centauri no longer feels like a simple backup Earth. It feels like a warning against easy imagination. The nearest system beyond the Sun is not a clean second solar system waiting to be opened. It is a layered gravitational neighborhood, a place of bright stars, faint signals, moving shadows, and incomplete evidence. The more scientists study it, the more the nearest doorway becomes a maze. That is the final unease of Alpha Centauri. Distance did not have to be enormous to preserve mystery. Even the closest unknown can remain deeply strange. Alpha Centauri may become the first nearby planetary system humanity truly studies in detail. For thousands of years, it was only a bright point in the southern sky. Sailors could use it. Astronomers could measure it. Ancient observers could see its light without knowing that the point contained more than 1 star. Now that same point has become a whole system. 2 bright stars orbit each other every 80 years. A faint red dwarf sits far outside them. At least 1 confirmed planet moves around Proxima Centauri. A possible giant planet may be hiding near Alpha Centauri A. Smaller worlds may still be buried inside the glare. The distance remains about 4.3 light years. That is close on the scale of the galaxy. The Milky Way is about 100,000 light-years across. Alpha Centauri sits so nearby that its light reaches Earth in a little more than 4 years. A signal sent from Earth tonight would reach the system before a child starting school today finished elementary school. That kind of closeness makes it feel almost reachable. Then the miles return. More than 25 trillion miles separate Earth from Alpha Centauri. Voyager 1 has traveled since 1977 and remains only a tiny step into interstellar space compared with that distance. Even a laser-driven probe moving at a fraction of light speed would likely rush through the system in a brief flyby. The nearest doorway stays open only through light, mathematics, and patience. Still, that may be enough to change astronomy. Future telescopes may measure Proxima b more carefully. They may search for carbon dioxide, water vapor, methane, or other gases in a possible atmosphere. They may test whether heat moves from the star-facing side to the dark side. They may learn whether Alpha Centauri A has a giant planet, and whether that planet has moons. They may find smaller rocky worlds around one of the bright central stars. A detailed map could begin to form without a spacecraft ever slowing down there. That map may be stranger than the one people expect. Some worlds may be dead rock, some may be stripped by radiation. Others may hide under ice, beneath clouds, or inside orbital positions where our instruments struggle to see them. A planet could be promising in temperature and hostile in radiation. A moon could be more interesting than the giant planet it orbits. A red dwarf world could hold its most important environments underground, protected from flares by rock and water. The closest system beyond the Sun may contain categories that feel unfinished. Not every world fits neatly into Earth-like lifeless, frozen, or habitable. Nature often fills the spaces between our labels. Alpha Centauri teaches that lesson gently but firmly. A habitable zone can hold a gas giant. An Earth-mass planet can orbit a flare star every 11.2 days. A possible world can appear in Webb data, then vanish into the star's glare months later. A system close enough to tempt us can remain difficult to read. This is the deeper meaning of the search. The nearest stars are not simple just because they are near. They are physical places with their own histories, motions, weather, gravity, and violence. They have spent billions of years evolving without reference to us. Our telescopes are only now becoming precise enough to notice the faintest pieces of that story. Alpha Centauri is our nearest stellar neighbor, but it is also a reminder that the neighborhood around the Sun is still mostly unknown. Beyond Pluto, beyond the Oort cloud, beyond the fading signals of Voyager, the first other system waits in the dark with 3 stars and a growing list of possible worlds, close enough to study, far enough to humble us, strange enough to keep changing as our instruments improve. Tonight, Alpha Centauri looks less like a destination we have almost reached and more like the first true mystery waiting outside our own solar system. A nearby place filled with moving stars, hidden planets, dangerous light, and unanswered questions. And somewhere inside that distant glow, only 4 years away by light, the closest unknown worlds to Earth may still be waiting for us to notice them clearly.